Howdy. I'd like to take a couple of minutes to look at number 8 in the book. Number 8 asks about a conical pendulum. A conical pendulum has a mass that's on a bob. And the mass does not swing back and forth, but instead it swings around like so. And what we're given in the problem is a value for L and a value for theta. And then they ask these two questions. First of all, one, what are the horizontal and vertical forces of tension? We'll put that as what are the components of the tension in the rope. And the second question that they ask is, what is the radial acceleration? And they give a bunch of numbers, but we're going to solve this in symbolic form because we get more insight that way. And along the way, what I'm really aiming for with number 1 is to reinforce the idea of a side view and a bottom view analysis. And what I'm aiming for with number 2 here is to talk a little bit about being sure that you answer the question in the terms of the question. Okay. So we have this conical pendulum, and now what we want to do is to take a side view on it. And our side view looks like this. We have a mass, and we have a tension that's pulling along the string, and we have an mg that is pulling straight down. And that's really it for all the forces that we have on the bob. Our side view. Boy, that side is sad. There, that's better. And then, if I take a bottom view, then the mass is now going to be seen as going around in a circle from the bottom. In fact, if this is the radius of the circle r right here, and here's my mass, and here's that dotted line going all the way down, like so. And this would be the radius of the circle r here. This would be the radius of the circle r here, so we can see that my mass is going to go around in a circle something like this. And what are the forces acting on this mass? Well, if I look at it from the bottom, mg is coming straight out of the board at me. I'm not going to see that. But I will see a component of tension, which is the radial component of tension, that's going to be pulling in just like this. My radial component of tension is right here on this diagram. And this right here would be the vertical component of tension. We'll call that the z component. We'll scratch out our teeth. And so that is now a full accounting of the forces in our diagram. Now we're ready for sum of forces. And we're going to do, first of all, a sum of forces in the z direction from the side view. And when we do, we have tension in the z direction minus mg. And all of that must be equal to 0 because the bob is not accelerating. There is no acceleration in this direction. The bob is rotating in the plane. And then we're going to have the sum of forces in the radial direction. And that is going to give me only one force, which is TR. And because we are in constant circular motion, that TR must add up to mv squared over the radius. And now we're ready to ask some questions here. First of all, what are TZ and TR? Well, if this is my angle theta right here, then that same angle theta is going to be the angle theta right here, so that TR is opposite to theta, and TR is equal to T times sine theta. And meanwhile, TZ is adjacent to theta, so TZ is going to be T cosine theta. And therefore, it must be equal to mg. Well, this answers our first question. What are the components of the tension? The component of tension the tension itself is equal to mg divided by the cosine of the angle theta. And therefore, the vertical component tz is going to be equal to mg, as it must. And the horizontal component, tr, is going to be equal to t sine theta, which is going to be mg over cosine theta times sine theta. And that's, if we're going to simplify it, equal to mg tan theta. The second question is, what is the radial acceleration? R-A right there. The radial acceleration of the object. And here we want to be careful to answer in terms of the question, because I could actually give two different answers. I could give one answer and say that the radial acceleration is equal to v squared over r. But the problem with this answer is that it gives values that are not originally given to us in the problem. I could find those values, but that seems like a pain in the neck. So I look around and I see, is there any other way that I can find the acceleration in terms that are given to me? And I notice that I have the force in the radial direction, which is tr, and therefore I can also write that the acceleration in the radial direction is force divided by mass, which is therefore equal to g tan theta. And this is a much better answer because it answers in terms of fundamental constants and quantities given in the problem. So, I hope this was helpful to you.